Swayam Prabha. Digital India. Educated India.
So, welcome to today class of nonlinear vibration. So, last few classes we are studying the application of this nonlinear vibration, and particularly we have taken different systems. For examples, we have taken this cantilever beam. So, this cantilever beam can be base excited. So, for example, last time we have taken this magnetoelastic beam also. So, we have taken this beam as viscoelastic beam, magnetoelastic beam or the elastic beam. In all these cases, we have studied the nonlinear dynamics of the system. In some cases also we have applied this load. So, we have applied a axial load which produce actually or gives rise to parametrically excited system. Also we have taken in all these cases these base to be excited. In all these cases we have studied the nonlinear dynamics by first deriving the spatio-temporal equation and then converting that spatio-temporal equation to its temporal form by applying Galerkin method, generalized Galerkin method. And in this generalized Galerkin method, so we have used these assumed mode shapes, and for example, this is one of the temporal equation we have derived. After getting the temporal equation, then we have used this perturbation method, particularly this method of multiple scales, and consider different resonance conditions. By considering different resonance conditions, we have shown when the system will be stable, unstable, and also different bifurcation points. For example, so we have studied the pitchfork bifurcation points. So, it may be supercritical or subcritical pitchfork bifurcation points, then the saddle node bifurcation, and then Hopf bifurcation points. So, in Hopf also it may be supercritical or subcritical bifurcation, and previous to that is the pitchfork and saddle node bifurcation points are static bifurcations. This Hopf bifurcation is a dynamic bifurcation which gives rise to periodic response. So, later we have seen how this periodic response also bifurcates or it leads to period doubling and period doubling root 2 chaos. So, by doing this Poincare section or by using this Poincare section, so we have characterized the fixed point, periodic, quasi-periodic and chaotic responses. For example, in case of periodic responses, so we have in a single period, so we have only single dot point in the phase portrait while we are drawing the Poincare section. Similarly, for two periodic we will have only 2 points. For multi-periodic, then it will have multiple points on the phase portraits, but if the response is chaotic, then it will fill up the whole space, and if it is quasi-periodic, then we have seen that we can have a closed loop in the phase portrait. So, that way we have studied different routes to chaos. For example, period doubling route to chaos, torus breakdown route to chaos, then torus doubling route to chaos. Also we have seen this crisis, for example, this attractor merging crisis, interior crisis, exterior crisis, and also we have seen this intermittency route to chaos in the simple cantilever beam when it is base excited. And where also we have considered, in addition to the external resonance conditions, so we have considered the internal resonance conditions. So, in internal resonance condition particularly we have taken this 1:3 internal resonance conditions, 1:3:5 internal resonance condition when we are considering 3 modes, and 1:3:9 also in case of 3 mode interactions we can find. Similarly, in case of the viscoelastic beam, so we have used this concept of loss factor, and there we have seen how we can decrease or increase the amplitude of response by changing different system parameters. Similarly, in case of the magnetoelastic beam, so by applying magnetic field we have seen the parametric instability region. So, today class we are going to study or will extend that same system by putting a piezoelectric patch on that thing. so which can be used for the energy harvesting purpose. Today class particularly we will see this energy harvesting, and in addition to that we will see a sandwich beam also. So, how we can analyze a sandwich beam, that thing you can see. So, in this magnetoelastic beam, so applying different magnetic field. So, already we have seen how the frequency response can be controlled, or the how the response amplitude can be controlled. So, for example, without magnetic field, so you have seen this black frequency response curve. Now, by applying a magnetic field of 0.3, this pink color, and then finally by applying a higher order magnetic field, so it has reduced further to this thing. If we have a magnetoelastic beam, then by easily applying magnetic field, so we can control the vibration of the system. So, this is happening as the stiffness of the structure we can control by applying this magnetic field. When we have multiple solutions, so by using this basin of attractions, we can study the different responses, and these are the publications by my PhD student Varun Pratihar. So, related to elastic, viscoelastic and magnetoelastic beams. So, in all these cases you can see the single link manipulator, how it can be used for vibration control. So, these are the papers by Professor R.C. Kaur and myself. So, these are on these internal resonance conditions. So, several papers are there published in Journal of Nonlinear Mechanics, Nonlinear Dynamics, then Journal of Sound and Vibration. All these papers you can refer to have a better understanding how you can convert a continuous system to that of a discrete system, and then how to analyze to get the complex nature of this nonlinear vibration. Let us come to today class, where we are going to discuss regarding the nonlinear dynamics of piezoelectric based energy harvester. Here the same system we are taking, but by applying this piezoelectric patch on that thing. So, we will see how it can be used as the harvester. Energy harvesting is the process by which energy is extracted from the external source and stored in the other form of energy. These external sources are divided broadly into two categories. One is this high level energy source like the solar, wind and tidal, and this low level energy source like this vibration, heat and noise. From the ambient energy, so we can extract the energy by using this energy harvester, and then we can convert that thing to AC DC converter and regulator circuit with a storage component. Then that low power electronic device we can use to utilize this harvested energy. As these are the low power energy, then we can particularly use them in remote sensing applications, including automobile electronics, wireless sensor nodes to sense environmental condition, structural health, biological condition and automobile health, and many other applications also it can be used. These are the cases where we require this sub milliwatt power level to function. For example, these wireless sensors, data transmitter, controllers, medical implant, particularly these pacemakers, spinal simulator and electric pain reliever. So, here we required very less power. So, in all these cases, or health monitoring of structure and machines. So, you can see all these papers where these applications are clearly written. There are many structures where the sub milliwatt power can be utilized sensing purpose. This energy harvester can be utilized there very effectively. For example, this is a pacemaker. So, here also while walking, the slabs were installed at the London Olympic Games, where by walking we can generate this energy harvesting. So, these are the piezoelectric generator for road, rails and runway. So, we can utilize here also the piezoelectric energy harvester for getting this energy. Similarly, in the leaf spring of a automobile, we can put the piezoelectric patch, as the leaf spring is subjected to this bending. Here this piezoelectric patch will be, so piezoelectric patch can sense that vibration and or sense that bending, and due to this bending this voltage will be generated and that voltage can be harvested. Similarly, in other type of spring, in shock absorber or this energy harvesting circuit also you can use a energy harvesting circuit. So, you can use this hybrid energy harvesting device. There are several energy harvesting devices are there. So, you may use this piezoelectric type energy harvesting or magnetoelastic type energy harvesting. So, we will see one by one. And so, this power density comparison you should know. So, the vibration power density in ambient is about 200 to 300 microwatt per cm3. Acoustic noise contain this 0.003 microwatt per cm3 at 75 dB, and similarly 0.96 microwatt per cm3 at 100 dB. So, you just see by increasing this noise, so we can increase the power density. Similarly, temperature variation. So, for temperature variation we can get 10 microwatt per cm3. Ambient light can give 100 milliwatt per cm square. So, direct sun we can get this 100 milliwatt per cm square. So, then vibration piezoelectric base we can generate 200 to 300 microwatt per cm3. So, these things you can find in this paper, released 2007. So, in the last portion of this presentation I will show you the references where you can get the details of this reference. So, vibration is one of the harvestable ambient energy. Vibration energy produced by all man-made structure and human beings during natural activity can be used for the harvesting the energy. There are several conversion mechanism. For example, this electromagnetic conversion, one can do this electromagnetic conversion. We can use easily this Faraday concept, Faraday principle to generate this thing. For example, so at the end of the cantilever let us have a magnet and we have a coil here. So, when the beam is vibrating, this magnetic field is changing. So, the flux caught inside this coil is changing, and due to the rate of change of this flux in the coil, EMF will be generated. So, this EMF can be harvested or can be taken for different application purpose. Similarly, we can use this electrostatic or this capacitive type of conversion mechanism where we have a proof mass. So, proof mass is supported by the spring. As this proof mass is moving up and down, the gap between these two capacitive or capacitor can be changed. So, you can see with this proof mass there are some additional structures are there. So, by the movement of the proof mass there will be variation in the gap between the capacitor plate. So, that will give rise to EMF, and that EMF also can be harvested. We can have this electromagnetic way, piezoelectric magnetic way, or this electrostatic or capacitive way of generating this or harvesting the energy. So, if we are taking, so this is typical piezoelectric slab. So, in this piezoelectric sheet the property, for example, this has a length of 5 cm, its width is 2 cm and thickness equal to 0.16 cm. So, this patch we have purchased and it has been used in our experimental setup for harvesting this energy. While using this piezoelectric patch, so we should know that in this piezoelectric patch, so the strain is due to both electric and due to this direct bending of the beam. So, one is due to direct bending of the beam and another part is due to this electric part. So, the strain can be retained. So, this is due to stress component and this is due to electric component. So, we can find this constitutive equation, that is reduced equation. Here you can write this between strain. So, stress component is T here, strain component is S, electric field component is E and electric displacement component is D. So, by using this thing, the stress strain relation can be, so this is the strain component and this is the stress component can be retained by using this matrix, and by using this one, so we can easily derive this equation of motion. Okay, so you can use, for example, this PZT, lead zirconate titanate, coupling mode will be D31 or D33, then PVDF, then direction of force and pulling directions you can see, then MFC, microfiber composite. So, this is the MFC patch you can see. Then we required AC to DC converter also for all this conversion mechanism. So, classification, so we can have a excitation. So, direct parametric It can be direct excitation, it can be parametric excitation, it can be random or simultaneous. Of all these excitations also can be applied to a system to harvest this energy. So, in case of direct, for example, we can give this wind force, or we can put it on a shaker or a vibrating structure, and in case of parametrically excited system, the direction of the force and the direction of the response are taking place in orthogonal direction. And in case of random excitation, while we may have a deterministic, so we can have a random excitation like the earthquake type of excitation, or sometimes there are many other phenomena which contribute to this random excitation. This wind excitation also sometimes is this random excitation. So, we can add all these things and we can have a simultaneous combination of all this direct, parametric, random, or direct and parametric excitation. Particularly for this easy analysis purpose, we generally take this direct and parametrically excited system, and also random excitation can be taken separately for this analysis purpose, or this random excitation can be converted to equivalent direct and parametric excitation to study the phenomena. So, we have a energy harvesting system, then so the system study may be linear, though actually the system is nonlinear. Many times it can be studied as a linear system. Sometimes or few researchers have taken this as a nonlinear systems. So, with or without internal resonance conditions also it can be studied. Generally, when you are taking this as a continuous systems, so the for analysis purpose it can be converted to a single mode or multi mode, like what we have seen in previously when we have considered the internal resonance conditions. So, if we are not considering internal resonance conditions, in that case only single mode approximation may be possible, but when we are considering internal resonance condition, then multi-mode approximation, we may go for this multi-mode approximation and take the number of appropriate modes, particularly when we are modeling the system using a finite element method. So, we can easily go for multi-mode approximation and we can analyze the system for different resonance conditions. Already you are familiar with the resonance condition. For example, we have the simple resonance condition, then principal parametric resonance condition of first mode, second mode, third mode, so or the nth mode, then combination parametric resonance conditions. So, where we can have combination of first mode, second mode, combination of second mode, third mode, combination of first and third mode. So, that way, so we can have the combination parametric resonance of some type, difference type, and also in addition to this, we can, due to the presence of nonlinearity, so we can have subharmonic resonance condition and also superharmonic resonance conditions. So, let us come to our system. So, this is the schematic representation of a piezoelectric energy harvester. So, this is the substrate, that is the main body, and we are so this is the substrate part, this inside part is the substrate part, then these piezoelectric patches are put on both the sides of this thing, this substrate, and then we have a attached mass. So, the mass can be attached at any arbitrary position. So, previously we have seen by putting this mass at any arbitrary position, we will be able to generate internal resonance conditions. So, we can adjust this mass in such way that between the ratio of the frequency between any two modes can be controlled or can be taken in the form of integer relation. So, in that case we can have the internal resonance conditions, and here, so at the base side the moment will be large. As the moment will be large at the base side, so the strain will be more, stress will be more. As we know, m by I equal to sigma by y. So, m by I, that is m by I equal to sigma by y equal to E by R. So, in case of bending we know this relation. So, our sigma will be equal to m y by I. So, bending moment will be maximum at this free end, fixed end. So, bending moment is maximum at the fixed end. So, sigma will be maximum there, and as the sigma is maximum there, strain also will be maximum there. So, we can generate the voltage, more voltage at this position. So, we can put a circuit here to generate or tap that energy which is produced by this piezoelectric patch. Here we have a capacitive, we can have a load or we can have a capacitive type of circuit to store this energy or utilize this energy. So, now like in the previous case, here also we can derive this equation motion by either using this Newton's second law or by using this Hamilton principle or the energy based principle like Lagrange principle also by using this Newton or D'Alembert principle. So, we can write M equal to, that is bending moment at a section S can be written as M1 plus M2 plus M3 plus M4. So, that thing we have seen previously at any position S. So, this is position S, this mass is at a distance d. So, we have taken a dummy position zeta, we have taken, and then this is d zeta, a small element d zeta we have taken. So, like previous case, so we can derive this M1, M2. So, M1, M2, M3, V is in the transverse direction. So, we have taken this transverse direction, then axial direction. So, axial direction displacement is u and this transverse direction displacement is v. So, first we have to take the inertia force in the transverse direction. So, this M1 is due to bending due to the transverse direction forces. So, this is equal to rho plus m delta zeta minus d v double dot plus c v dot. So, into that distance. So, that distance equal to s to zeta integration s to zeta cos phi d eta. So, this d eta is the dummy variable into d zeta. So, this is M1. Similarly, M2 is due to u double dot, that is in, so that is in the axial direction. So, in axial direction also you have the weight. So, that g component is coming here. So, rho plus m delta zeta minus d into u double dot minus g into the bending part. So, this is the force acting into distance will be the bend, will give the moment. So, s to zeta sin phi d eta d zeta. Then due to this rotary inertia part, this M3 will be there. So, j delta zeta minus d phi double dot d zeta. So, this is the rotary inertia part due to the attached mass. Then finally, for the piezoelectric patch, so we have another equation, that is M4. So, M4 will be equal to sigma p into Bp y dy. So, then this is sigma p Bp y dy for the piezoelectric patch. So, we can have, so we can divide that into two parts and we can derive this equation motion. Actually, if we double differentiate this moment equation, then we can get this forcing equation. So, differentiating twice that equation, so we can get the equation in this form. So, then for the circuit, so this is one equation we got. So, now for the circuit, so we can draw the circuit diagram, and for the piezoelectric patch, so we can write the equation motion. So, this equation is Cp by 2 d Vt by dt plus Vt by R minus Ipt equal to 0. So, this is using this Kirchhoff's voltage law. So, you can easily derive this one. Then where n equal to this and all these equations are, you can easily derive. So, these are the boundary conditions also we obtain. So, when you are applying this Hamilton principle, the boundary conditions you can get it along with the equation motion. So, now generalized Galerkin method can be used. So, if you compare this equation with the previous equation what you have derived, so here due to the presence of the piezoelectric patch, so we have the electromechanical component present in this case. So, now by taking this Vst equal to, that is this displacement, it is a function of both s and t, that is space and time. We can write it equal to n equal to 1 to infinite r psi n s q n t, where r is the scaling factor and psi n s is the shape functions and q n is the time modulation. So, the psi n we can take it from that of Zabodini and Nafe, where it is derived for the mass at arbitrary, by keeping the mass at some position. So, the psi n s can be written here. Then using this non-dimensional term, for example, this non-dimensional distance equal to s by l, then non-dimensional position beta equal to d by l, tau equal to theta 1 t. where theta 1 is the frequency of the first mode, tau equal to theta 1 t, omega n equal to theta n by theta 1, lambda equal to r by L, mu equal to mu m by rho L, mu is the mass ratio, and capital gamma equal to Z0 by ZR. So, Z0 is the base excitation, amplitude of base excitation, and ZR is the reference amplitude we have taken. So, J equal to J0 by rho L R square and phi equal to omega by theta 1. So, this way by using different non-dimensional parameter and using this single mode, one can use multi-mode approximation or single mode approximation. So, for the displacement, similarly for voltage we can write voltage Vt equal to Rv into Vt, V bar t. So, we have used this non-dimensional term. Now, by putting all these non-dimensional term, so we can derive this equation motion which can be written in its temporal form in this way, that is q n double dot plus 2 epsilon zeta n q n dot plus omega n square q n plus epsilon k j m. So, if we are taking only 2 mode, then this k j m will vary from 1 to 2 alpha k element q l q m, then beta k element q l dot q m dot, then gamma k l m n. So, q 1 q m double dot into q k. So, outside this q k is written. This shows that these are cubic nonlinear terms we are taking. In this the first term q l q m and into q k, that is geometric nonlinear term, and then q k into q l dot into q m dot is the inertia nonlinear term due to the multiplication of two velocity term. Similarly, this gamma n k element into q l into q k into q m double dot, this is the inertia nonlinear term. Similar to the previous paper, we have both geometric and inertial nonlinearity here. So, plus epsilon eta v Vt. So, this is the voltage term. You just see in the first equation we have a coupled electromechanical system, electromechanical coupling. So, due to the presence of this term, that is epsilon eta n v tau. So, this is the voltage term, electric term. So, it is coupling both these equation, that is this mechanically excited term or mechanically vibrating term, that is q, with this v, minus this is the forcing minus epsilon m equal to 1 to 2 f n m q m equal to 0. So, similarly, this is the voltage equation. So, voltage equation equal to v dot tau plus xi v tau plus n equal to 1 to 2 k n q n dot equal to 0. We can apply the inextensibility condition. So, here, so you can note that we have applied this inextensibility condition, that is u zeta t equal to zeta minus 0 to zeta integration 0 to zeta cos phi eta t d eta plus z t. So, we have used this inextensibility condition to derive this equation motion. Also, we have taken this z t equal to z0 cos omega t in this analysis. So, now after getting this governing equation in temporal form, so we can apply the perturbation solution. For example, here we can use many other method. For example, one may use this normal form method, harmonic balance method, Lin-Stead-Poincare method, KBM method, this homotopy method. So, many methods are available, or simply by using this RK4 method, Runge-Kutta, fourth order Runge-Kutta method. So, one can find the response of the solution, particularly if you are using this Runge-Kutta fourth order, fifth order Runge-Kutta method, then you can get the response of the system for a particular system parameter. For example, so if one has to obtain the frequency response plot from the time response, one has to spend huge memory space and also time to get that simple frequency response plot. For this purpose, so one has to go for the perturbation method, so that easily one can plot the frequency response, force response, or study the variation of different system parameters with the given system parameter. Now, applying this perturbation technique, for example, taking this method of multiple scale, we can write down this Qn0 equal to An e to the power I omega n T0 plus Cc, and then V0 equal to minus n equal to 1 to 2 Kn Zn An T1 e to the power I omega n T0 plus Cc, where Cc represent the complex conjugate of the preceding term. Whatever terms are there before the Cc, all the terms have the complex conjugate. The Cc represent the complex conjugate of the preceding terms. Here we can consider the internal resonance condition and external resonance condition. Particularly if you are interested for principal parametric resonance condition, so we can have this phi equal to 2 omega 1 plus epsilon sigma 1 and omega 2 equal to 3 times we are taking this internal resonance condition, omega 2 equal to 3 omega 1 plus epsilon sigma 2. So, where sigma 1 and sigma 2 are detuning parameter, detuning So, detuning parameter gives the nearness of the external frequency to the twice of the natural frequency. Similarly, the sigma 2 gives the nearness of the second mode frequency to 3 times of the first mode frequency. For example, let omega 1 equal to 2 hertz, so 2 radian per second. So, in that case omega 2 will be equal to 3 times, that is 6. So, plus minus epsilon sigma 2. By taking 10% of this 6, then we can go. So, we can vary it from, for example, 5.4 to 5.4 radian per second to 6.6 radian per second. So, we can vary this thing and we can find the response near to the principal parametric resonance conditions. So, here by substituting n equal to 1, so as we are going for 2 mode interaction, so we can substitute n equal to 1, n equal to 2, we will get actually 5 reduced equation in this case, proceeding in the previous case by using this method of multiple scale. So, we can get 4 equations for this amplitude and phase motion of the beam plus 1 equation for the voltage generated voltage. So, we will get 5 equations and solving those 5 equations. So, we can find the response of the system. Similar to the previous case, here we can make the transformation Pi equal to Ai cos gamma I and Qi equal to Ai sin gamma I. So, where I equal to 1 to 2. So, we have these 4 points. So, this Pi Qi conversion is taking place to have the trivial state instability region. So, to study the trivial state instability region, generally we convert this thing. So, to study the trivial state instability, generally we convert this to Pi and Qi form. These are the equation one can obtain using this Pi and Qi form. So, P1 dash, Q1 dash, P2 dash and Q2 dash, and then one can do the stability analysis by perturbing these equations. So, by perturbing these equations one can find the Jacobian matrix, and by finding this Jacobian matrix then one can find the eigenvalues of the Jacobian matrix. By finding this eigenvalue of the Jacobian matrix, if the real part of the eigenvalue lies in the left hand side of the S plane. So, left hand side of the S plane, then the system is stable. So, this is real. So, this is imaginary. So, if it is lying in the left hand side of the S plane, then it will be stable, otherwise it is unstable. One can study the stability and bifurcations of the response. So, one can convert after getting this displacement, one can find the voltage equation in this way. After getting this voltage equation, one can find the power, and so this is the power expression. So, depending on the resistive, capacitive and inductive circuit, the power will be different, and this is the expression for power one can get. Let us see some of the results. For example, so if we are taking material property what is taken. For example, for piezoelectric pads the material property EP can be taken, Young's modulus can be taken 15.86 GPa. For the substrate like this aluminum, so it is 190 GPa. So, you see this piezoelectric patch has very less Young's modulus. This density of this piezoelectric patch is 5440 and for the substrate equal to 7800. Similarly, length is taken. So, 12.54 into 10 to the power minus 2. So, this is in meter. So, if we are considering the full length of the beam, then we can take both LP and LB same, width also 1.12 into 10 to the power minus 2 meter. So, width of the substrate is taken slightly more, this is 1.22 into 10 to the power minus 2. Thickness of the substrate part is taken 1.25 into 10 to the power minus 4, and then this is for the piezo patch, and for the substrate it is equal to 3.7 into 10 to the power minus 4 meter. The permittivity is taken 19.36, piezoelectric constant coulomb per meter square, E31 is taken minus 19.84. These parameters are similar to those available in many literature. So, taking all these parameters, so one can easily plot the instability region. So, one can see these are different instability region, and with different value of this nu, that is damping parameter. So, one can see the instability region moves up. That means, for example, if you are taking this nu equal to 2.5, then below this gamma equal to 10, always whatever may be the value of the excitation frequency pi, the system will remain stable. Only we should be bothered, or it can be used as a energy harvester only if the excitation amplitude is greater than 10. Otherwise, for nu equal to 2.5, it cannot used as a energy harvester. Actually, this unstable position, when the system becomes unstable, this is the position where we are using this as a energy harvester. This is the, so in stable region actually it cannot be used as a energy harvester because it will not vibrate. When it is trivially unstable, so that configuration we have to take to use this as a energy harvester. You can see by using these internal resonance conditions, for example, here or here. So, you can see we have multiple regions. So, multiple regions where it can change from stable to unstable, and we are particularly looking for the region when this system becomes parametrically unstable, and we can use that region only for this vibration or energy harvester purpose. So, when it is in this region S trivially stable, so that means it is not vibrating. So, if it is not vibrating, so it cannot be used as a energy harvester. So, in the previous cases we have seen, or we have checked the condition where the system will be stable, or we are interested to know when the system will be stable, but in this case we are interested when the system becomes unstable, when the system becomes trivially unstable, because this trivial unstable configuration will give rise to this energy harvesting condition. So, the system we can harvest the energy when this is inside the instability region or the parametric instability region. So, you can see these are the time response one can obtain for different value by putting different value O1, O2, O3 what we have seen here. So, this is O1, O2, O3. So, here O1 and O3 are stable region. So, in case of O1, O3 you just see it is stable, and finally it is 0. So, it is in trivial state, it is not vibrating, but when it is operating in O2, the system response you can see. So, this is chaotic response and it is system is unstable, but we can generate very high voltage due to the vibration. So, we have a very high amplitude of vibration in this region. So, you just see for the same system parameter here we are taking O1, O2, O3 have the same value of gamma, but this phi is changing. So, O1 is in the stable range, O3 is in the stable range, and O2 is in the unstable range, parametric instability region. For if we are operating this at O1 and O3, the system will not vibrate in its steady state, but if we are operating it at O2, then the system will vibrate and we can use that as a energy harvester. That magnitude of the vibration can be obtained from the frequency response plot. For example, in this particular case, for example O2, so if we are taking phi 2 near to 2.2, phi 2 nearly equal to 2.2, we can find what is the response amplitude. So, the response amplitude is shown to be around 20, 22. So, it will go on increasing also depending on the other system parameter. Okay. This way we can find the frequency response. So, frequency response actually can be plotted by solving these 4 or 5 equations what we have seen, reduced equation in first order reduced equation. By solving these nonlinear equations by using Newton's method, so we can find or we have plotted these frequency response plot. So, while plotting this one, we have taken several initial conditions. So, there are several methods to plot this thing. So, later you will know or you have known by this time this continuation principle also, continuation technique to get the response. By using different technique, you can find the frequency response plot. But in this particular case, we have taken a large number of initial conditions and used this Newton's method to find the response of the system. So, in that way frequency response has been plotted. So, these are the frequency response for different value of this nu and gamma. So, for example, nu equal to 0.001, gamma that is the base excitation equal to 1, this is the non-dimensional parameter. Similarly, R load resistance is taken to be 1 kilo ohm. In that case, we have obtained this voltage. So, you can see we can obtain very high voltage in this case also. So, the last curve shows the power. So, power we are obtaining some in terms of the watt, few watt power we are getting in this case. By changing different load resistance or changing different value of gamma and nu, we can have different frequency response, and from those frequency response we can find exactly how much energy we can harvest or what is the voltage we can get and how much power we can generate for different system parameter, taking a large number of system parameters. Here all these plots have been plotted. Those who are interested to know more regarding this thing, so they can study this system, they can physically derive these equations and simulate these equations to find this response. This will be given as an assignment to find the frequency response and force response in case of the energy harvester. We have seen now, so we can use this energy harvester for getting this voltage and power, and there are several papers available, and you can particularly see there are several recent papers available on this energy harvesting. So, these are the paper you can published in 2021. For example, this nonlinear modeling design and parametric study of an effective harvester in large amplitude vibration using magneto-electric transducer. So, here we have used this piezoelectric transducer. One can use the magneto-electric transducer, where one magnet can be used, it can be electromagnet or it can be permanent magnet. So, that electromagnet or permanent magnet can be used and a coil will be there. So, due to vibration this field will change and that will help in generating this voltage. This is a very recent paper, you can go through it, and this one more paper by Bao and Wang, a rain energy harvester using a self release tank. So, it is published in Mechanical Systems and Signal Processing. Then Kai and Leo, they have published another paper, enhanced electromagnetic rest or energy harvester using repulsive magnetic spring. So, you just see here the harvester is put on the wrist. So, from the body motion also we can harvest the energy or generate the energy. Another paper also you can see, a low cost alternative lead free piezoelectric material for vibrational energy harvester. We are using particularly this PVDF or this PZT where we are using this lead. So, this paper tells about lead free piezoelectric material. Then another paper you can see, this is a comb like beam based piezoelectric system for galloping energy harvesting. So, this is a very recent paper. So, a number of beams are used for harvesting this energy, and then a system of characterization of piezoelectric material and associated electronics for vibration powered energy harvesting devices. This is also a very recent paper. Optimal design and experimental verification of piezoelectric energy harvester with fractal structure. This is published in Applied Energy. So, you can go through this one also. A hybrid piezoelectric wind energy harvester for high performance vortex induced vibration energy harvesting. So, here this galloping method is used for generating the or harvesting the energy. Then modeling of piezoelectric energy harvester for medical applications using intelligent optimization techniques. Then you can see also the enhancing energy harvesting in low frequency rotational motion by a quad stable energy harvester with time varying potential well. So, these are the recent publications what I am showing. I have taken it from Scopus and just created this bibliography of the recent paper. So, some of the more recent papers are model based design and variable speed, non-salient pole permanent magnet synchronous generator for urban water pipeline energy harvesting, then nonlinear modeling and performance testing of high power electromagnetic energy harvesting, system for self powering transmission line, vibration dicing robot. Then you can have this design and analysis of a broadband 3 beam impact piezoelectric energy harvester. So, here we have taken a single beam. So, you can take 3 beams or you can take multiple beams also to harvest this energy. So, multiple beams can be taken to harvest the energy also. Then design and development of novel 2 directional energy harvester with single piezoelectric stack. Then EXO SU triboelectric magnet nano generator. So, here you just see these are the wearable devices towards high performance wearable biomechanical energy harvester. Then modeling and analysis of an electromagnetic vibration energy harvester for automotive suspension. In the beginning I have shown how you can put this piezoelectric patch on the leaf spring, also how you can put them on the helical spring in the shock absorber also. So, there are some other paper, for example, design modeling and experimental validation of a low frequency cantilever triboelectric energy harvester. Similarly, you can have many other, you can source many other paper, you can see some of the paper related to energy harvesting are shown here. So, you can take any of them and go through it and see this thing. Here also we have developed this galloping based piezoelectric energy harvester. In case of galloping, in this same cantilever beam, bottom part we can put the piezoelectric and here we can put a bluff body. When it is put in front of the wind, then due to the obstruction by the bluff body, so wake formation will be there in the back side and this will give rise to this vortex induced vibration in this case. So, these are some of the references related to galloping based energy harvester. One can go through all these papers. So, many references have been given, the basic principle remaining same, but the forcing part will be different. So, in this case due to this wind force, forcing term can be taken. In the previous case we have given the axial loading and base excited system. So, from there forcing term were generated. Here one can see. So, this is the bluff body, just we have put in front of the UPS. So, from the UPS this air is coming which is vibrating the structure. So, as it is vibrating, so you can see energy is generated, voltage is generated, which we have shown through this oscilloscope. So, experimentally we have shown this voltage generation due to this galloping phenomena. Now, briefly let me tell how you can use similar concept. So, you have seen now we have 3 layer, 2 piezoelectric layer, and in between we have the substrate. So, similarly, so those are sandwich structure. So, these are sandwich structure. So, in this sandwich structure, so we can have a top skin, also a bottom skin, and in between we can have the viscoelastic layer. So, in this viscoelastic layer we can make this magneto-rheological elastomer. So, in case of magneto-rheological elastomer, so this is the elastomer, that is viscoelastic material. So, while curing, so we used to put this iron particle, and after it got cured, this becomes this MRE, magneto-rheological elastomer. So, by applying this magnetic field, so one can find or you can align this magnetic field or this iron particle. Due to this alignment of the iron particle, the Young's modulus, which is a complex number, changes, that is the stiffness and the damping property of the material changes. So, we can have different skin material and also different core materials. So, you can go through all these things. So, there are several advantage and disadvantage of this thing, magneto-rheological elastomer. So, this is the basic principle already I told. Okay, so, there are two different type of MRE, one is the isotropic MRE, second one is the anisotropic MRE, and you can see by applying temperature we can change this loss factor and storage modulus. Similarly, by applying magnetic field also we can have the storage different shear modulus and loss factor. So, this is the magnetic field strength. So, we go on applying this magnetic field strength, and we can see the shear modulus is changing. So, here the loss factor is also changing. So, initial loss factor and final loss factor, if you see, then we can increase it 2 times to 3 times also, or 1.5 times. Here it is shown for this case, it is 1.5 times. Here also you can see this is 1.5 to 2 times also we can increase the shear modulus, storage modulus. By changing this shear storage modulus and also this loss factor, so we can control or we can make the sandwich beam as this a smart material. So, here we can use different percentage of iron particle, different percentage of this carbon black, and we can change this material property and we can develop our own sandwich structure, and we can apply different classical theory or superposition approach or higher order theory, and we can study the system. So, if the system is subjected to one axial load, so there are several literature available here. So, these are literature, some of the literature have been shown here. In this particular case, let us have a sandwich beam where this is subjected to axial loading and this magnetic field is applied. So, we can have different boundary conditions. So, for different boundary conditions, you can derive this kinetic energy, potential energy, then this loading due to. So, if we are taking the skin material to be conductive, then we can have the Lorentz force and couple. We can find this N and this force and this couple, and due to that thing this axial loading will be there, and we can find the non-conservative work done, and using extended Hamilton principle. So, we can derive this equation motion. So, after getting this equation motion, we can apply equation motion will be in the form, it will be spatio-temporal equation. So, now you can convert that thing to its temporal form by using Galerkin method. So, which will reduce to this form. So, where this M is matrix K11, K12, so all these are matrix. So, Q1, Q1, Q2, so these are the state vectors. So, you can see due to the presence of the storm P1F Q1, where Q, this coefficient of Q1 equal to P1F, so which is a time varying function. So, this is a parametrically excited system. So, in this parametrically excited system, you just see this K equal to stiffness part K11 minus P0F minus K12 K22 inverse into K12 transpose. This way we can write down this equation, and different elements of different matrix can be found here. Actually, you can go through detail of this work in the work of Naik, Vishwajit Naik, who was my PhD student. You can get this reduced equation Now, using this reduced equation, so we can use this modified Su method to find the instability region. So, we can find this instability region. So, these are the equations already given there in this modified Su method. By using this modified Su method, we can find the response of the system, and if we can do this experiment, for example, let us take the cantilever beam and put accelerometer here and accelerometer here. For the top accelerometer and bottom accelerometer, if you see this acceleration versus frequency, you can see they are matching. So, one can use a classical theory for this type of analysis also. You can see the response also for the top skin and bottom skin. So, now you can see the response without applying voltage and without applying magnetic field and with applying magnetic field. So, it is clearly evident that by applying magnetic field we can reduce the vibration considerably. Here it is more clear. So, you can see the vibration is reduced and the settling time, we can reduce the settling time very much. So, in the first case while it is, so without you just see, so it is vibrating up to this, but when you are taking with a magnetic field, you can see the vibration is settled down here. So, we have a settling, and this peak value is also very less. Without magnetic field, peak value is very high, and with magnetic field it is very less. So, this way you can control the vibration of a sandwich beam by applying this magnetic field. So, this is the instability region you can plot with different effect, different carbon block you have put, iron particle, and also you have put magnetic field. So, by putting magnetic field, different iron particle and different carbon block, percentage of carbon block. So, you can see the response amplitude can be conveniently controlled. So, if it is operating in this instability region inside this thing, then one can find the response amplitude will grow. So, clearly this shows the response is growing. So, if you want to use this as a energy harvester, then you can use it inside this unstable region. If you want to use this as a for controlling the vibration purpose, then you can use in this stable region. One can observe this beating type of phenomena also. So, these are some of the references you can see with this thing. So, let us conclude this session here. Now, you know how you can use a continuous system for analyzing that as a nonlinear system. So, you can reduce that spatio-temporal system to its temporal form by applying Galerkin procedure. So, then getting this temporal equation, so you can apply different perturbation techniques to find the nonlinear response of the system, and in this nonlinear response you can study different stability and bifurcations, and you can apply it for many different purposes as per the requirement. So, next class we are going to study some more applications. For example, we will take a multi-degree of freedom system, particularly we will take this vibration observer. So, a 2 degrees of freedom system will take this passive and active vibration observer and apply different control strategy to study the attenuation of vibration or absorption of vibration in this vibrating system. Thank you very much.